Have you ever wondered if light, the fastest thing in the universe, could travel backwards in time? This question might sound like it's been plucked straight from a science fiction novel, but it's actually a topic that has intrigued scientists for years. Let's start with a basic understanding of light. Light is a form of electromagnetic radiation that travels at an astounding speed, about 186,000 miles per second to be precise. This speed is so colossal that it has been used as a constant in the world of physics, famously featured in Albert Einstein's theory of relativity, E equals mc squared, where CE represents the speed of light. Now imagine this speedy light, not just traveling from point A to point B, but also journeying backwards in time. It's a mind-bending concept, isn't it? This idea isn't just a flight of fancy, but a theory grounded in the principles of quantum physics. Quantum physics, unlike classical physics, allows for the possibility of particles to exist in multiple states at once, and to influence each other instantaneously, no matter the distance. This opens up a whole new realm of possibilities, including the intriguing concept of light traveling backwards in time. This theory has been the subject of numerous debates and research. Renowned physicists like Albert Einstein, Richard Feynman, and John Wheeler have all contributed significantly to this field. They've questioned, debated, and hypothesized the nature of light and time, pushing the boundaries of our understanding and opening doors to ideas that challenge our perception of reality. It's important to note, however, that while this concept is fascinating, it's also highly theoretical and remains unproven. But isn't that the beauty of science? The constant pursuit of knowledge, the relentless questioning, and the thrill of uncovering the universe's secrets, one hypothesis at a time. Now that we've set the stage, it's time to delve into the experiments that have attempted to prove this intriguing theory. The Wheeler's delayed choice experiment is one of the most renowned studies in this field. Conceived by physicist John Archibald Wheeler, this thought experiment explores the strange and fascinating world of quantum mechanics. The experiment involves a light source, a beam splitter, and two detectors. The light source sends a single photon towards the beam splitter, which then has two paths to travel. One path leads to detector A, and the other to detector B. Now, here's where things get interesting. Before the photon reaches the detectors, a choice is made. If we decide to know the path the photon took, we place a device at the end of each path. When the photon hits one of the detectors, we know which path it took, and it behaves like a particle. But if we decide not to know the path, we remove the detectors. The photon then has to decide which path to take. Incredibly, it behaves as if it has taken both paths at once, like a wave. This is what we call wave-particle duality. So how does this relate to time? Well, the decision to measure or not measure is made after the photon has already left the light source, but before it reaches the detectors. It's as if the photon knows in advance whether it will be observed or not, and adjusts its behavior accordingly. This suggests that the photon's future affects its past, a phenomenon known as retrocausality. The implications of this experiment are profound. It suggests that at the quantum level, the distinction between past and future may not be as clear-cut as we think. It implies that light, in some sense, can go backwards in time. But the Wheeler's delayed choice experiment is not the only fascinating experiment in quantum mechanics. There are others that have also attempted to unravel the mystery of light's behavior and the concept of time. The implications of Wheeler's experiment are profound, but it's not the only experiment that has attempted to unravel this mystery. Another significant experiment in this field is the quantum eraser experiment. Now, this experiment is a variation of the well-known double-slit experiment. In the double-slit experiment, light behaves both as particles and waves. However, in the quantum eraser experiment, we add an extra twist, erasing the which path information that tells us which slit the light particle passed through. Picture this. We shoot photons one by one at a beam splitter, which sends each photon along one of two paths. Along each path we place a crystal that creates a pair of entangled photons. One photon from this pair continues along the path, while the other takes a detour to a second beam splitter. Here's where it gets interesting. This second beam splitter can either direct the detouring photon to a detector that records which path the original photon took, or it can mix the paths up, erasing the which path information. So what happens? When we observe the which path information, the original photons produce a particle-like pattern. But when we erase this information, the original photons produce an interference pattern, as though they had traveled as waves through both paths simultaneously. The most mind-boggling part? the decision to observe or erase the which path information can be made after the original photon has already hit the detector. This suggests that the act of measuring can retroactively determine whether the photon behaved like a particle or a wave in the past. This experiment, with its results, shakes our classical understanding of time. It implies that the future can affect the past, or that time can flow backward, at least in the quantum world. The quantum eraser experiment doesn't provide us with a time machine, but it does hint at the possibility of events unfolding in a non-linear fashion, challenging our everyday perception of time. These experiments are just a glimpse into the fascinating world of quantum physics. So, does this mean that time travel is possible? Now that's a question that has intrigued scientists and science enthusiasts alike for ages. Based on experiments like the Wheeler's delayed choice and the quantum eraser, it might seem like we're on the brink of hopping into our time machines. These experiments show that light particles or photons can behave in ways that suggest they can decide their past. This is mind-bending stuff that challenges our understanding of time and causality. However, before we get too excited, it's important to remember that these results are still confined within the realm of quantum mechanics, a world that is vastly different from our everyday reality. In the quantum realm, particles can be in two places at once or even teleport through barriers. But we're yet to see an apple both on the tree and in our hand, or teleport ourselves to the other side of a wall. Moreover, the idea of time travel brings with it a slew of paradoxes. Take the grandfather paradox, for instance. If you were to travel back in time and prevent your grandparents from meeting, you wouldn't exist. But if you don't exist, how could you have traveled back in time in the first place? Then there's the limitation of energy. According to Einstein's theory of relativity, the energy required to propel a human-sized object back in time would be greater than the total energy of the universe. That's a tall order, to say the least. Despite these challenges, the scientific exploration into the nature of time and the possibility of time travel continues. It's a thrilling journey, filled with exciting discoveries and profound questions. We're pushing the boundaries of our understanding of the universe, and who knows what we'll find. While the idea of time travel is thrilling, it's still a theory that needs more exploration. And that exploration, filled with curiosity, creativity, and rigorous scientific inquiry, is what propels us forward, or should we say backward. So, can light really travel backwards in time? That's the question we've been grappling with today. Let's take a moment to reflect on what we've learned. We began our journey with a look at light itself, exploring its unique properties and behaviors. Light, as we know, is no ordinary traveler. It moves at a constant speed, it doesn't age, and it can behave as both a particle and a wave. These properties open up fascinating possibilities when it comes to time travel. Then, we delved into Wheeler's delayed choice experiment. This groundbreaking experiment suggested that the behavior of light could be influenced by future events. It proposed that a photon could take two paths at once, and its state could be determined at a later time. This introduced the concept of retrocausality, where the future can affect the past. Following this, we ventured into the quantum eraser experiment. Here the concept of retrocausality was taken a step further. The experiment showed that not only could future events affect the past, but that this could be done without any signal traveling faster than light. This experiment challenged our conventional understanding of time, suggesting that the past, present, and future might not be as distinct as we once thought. Finally, we explored the reality of time travel. We discussed how these experiments and theories are reshaping our understanding of time and the universe. While time travel, as depicted in science fiction, remains elusive, the phenomena observed in these experiments hint at a universe where time is far more complex and malleable than our everyday experience would suggest. Today, researchers continue to probe the mysteries of light and time. New experiments are being devised, theories refined, and our understanding of the universe deepens with each passing day. The question of whether light can travel backwards in time remains an active area of research filled with intrigue and possibilities. While we may not have definitive answers yet, the journey of light continues to illuminate our understanding of the universe and time itself.
Please do like, share, and subscribe to my channel. Thanks for watching.